Okay, in this next little video clip we'll talk about resistance. But before we do that, let's quickly just recap that idea of voltage and current. So the battery is a source of energy, and it gives the electrons flowing through the circuit energy. So voltage provided by the battery is how much energy is gained, and we could measure the voltage drop, how much energy is lost by the electrons flowing through the bulb. Current is the rate at which the electrons flow, so how fast they are flowing around the circuit. So at any given point, like point A, we could measure how quickly the electrons are flowing past that point. But the two go hand in hand, because the more energy we give the electrons, the greater the voltage that's being supplied by the battery or the power pack, the faster the electrons will flow. So basically what we're saying is if we crank up the voltage, the electrons flow around faster, so we've also increased the current. But there's one more factor, one more piece to this puzzle, one more aspect that influences this too, and that's called resistance. So we've got a question here, and sorry, the numbering is a bit funny here, there's just two parts here. But if the bulb in this diagram were replaced with a bulb that had twice the resistance, how would that affect the current flowing around the circuit? So that's the first part here. How would that affect the current? Well, resistance is a property. It's how much a material or a component opposes the flow of electrons. So if we add a bulb that has twice the resistance, it will oppose the flow of electrons twice as much. So what that means is essentially resistance reduces the flow of electrons, whereas voltage, the amount of energy they're given, increasing the voltage increases the current, the flow of electrons. So they kind of work against each other. The greater the voltage, the faster they'll flow, but the greater the resistance, the opposition to that flow, the slower, obviously, the electrons will flow. So both affect the current. Current's kind of the result, the one that's altered as an effect. So if we have a look at this, for instance, our questions here. The first one, how would the current flowing through be affected if we replace this bulb with something that has twice the resistance? Well, twice the resistance means that the current will be halved. And that's essentially because if we've got twice the opposition, it's twice as hard to flow through this component. It will slow down those electrons. It will take twice as long for them to flow through. So increasing the resistance, the opposition to that flow of electrons, reduces the current. Doubling the resistance halves the flow. Just like voltage would have the opposite effect, if we doubled the voltage, we gave the electrons twice as much energy, they would also flow twice as quickly. So they all go kind of hand in hand together. So what would the voltage drop be across this bulb? How would that be affected? Would the voltage drop across the bulb be greater, less, or the same as previously? So let's pretend for a moment, we're just going to pull a value out of our heads and pretend that this battery is 12 volts. Now most of the cylindrical cells that look like this, your AA, your C and your D size batteries are actually 1.5 volts. But let's just pretend this one here is 12 volts. If the electrons going through this battery pick up 12 volts of energy, so it's each packet of electrons is getting, we would say, 12 joules of energy. I wouldn't worry too much about that. So that's just a measure of how much energy the electrons are gaining as they flow through here. When they go through the bulb here, because there's no other components, they're going to lose 12 volts of energy here. Now if we increase the voltage, if we put a 24 volt battery here, we would get 24 volts. All the energy is lost before the electrons return to the battery, and the bulb would simply glow brighter, or if it's too great, it might burn out the bulb. But essentially, increasing the voltage would increase the current. So in this case, increasing the resistance, it slows the electrons down, but it doesn't change how much energy they gain or lose at the battery or the bulb, respectively. So slowing the electrons down, having an opposition to the flow, doesn't change the fact that we've got 12 volts of energy being picked up by the battery and 12 volts of energy being lost at the bulb here. So just to sum it up, increasing the voltage would increase the current, increasing the resistance will reduce the current. Both have an effect on the current, how fast the electrons are flowing. And they have the effect is opposite. Increasing voltage increases current, increasing resistance reduces the current. Now resistance, so I should put the answer in there. So what would the voltage drop across the bulb be? Greater, less, or the same? It would be the same because the resistance doesn't affect how much energy is gained from the battery and therefore lost at the components. It simply affects the current, how fast they're flowing around. And that makes sense. I've often in my classrooms used analogies where students walking around a circuit are the electrons, and they carry energy, often give them M&Ms, represents the energy that they're carrying. And if a resistor, we get a bunch of students who try to stop them moving through, kind of act as a barrier. How strong the resistance is, or how great the resistance is, how great the opposition to that flow, only affects how fast the students move around the circuit, how fast the electrons flow around, and not actually the amount of energy they're carrying, the voltage. So the last one here, 6D, sorry, I'll just clear that. 6D, if current is graphed against voltage, so actually voltage, sorry, I should have said voltage against current, voltage on the y-axis and current on the bottom here, the slope of the graph actually represents the resistance. And that makes a lot of sense actually if you just stop and think about it for a second. Imagine we have a really steep line up here like this, a really steep line. What that's saying is that if we've got a really steep line like this, what it's saying is that a big voltage, a large voltage, so 6, if we go across kind of here to 6, only gives us a small current. If we come down here, we're only getting maybe 0.75 of an amp. So if we've got a very steep line, it means a big voltage, lots of energy, still only gives us a very a small current, a very slow rate of electron flow. So that must mean there's a big obstacle in the way. There's a lot of resistance or opposition to flow, because even though we're providing a lot of energy, a large amount of energy, we're only getting a small current. However, if I'll do it in a different color, if we have a very flat line like this, what that's saying is that even with only a small voltage, even if the electrons are only given a small amount of energy, say 1 volt, we're getting a reasonable or a larger current. You can see here, so if we put 1 volt in, we're giving the electrons 1 volt of energy, we're getting then 3 amps of current. We're getting a much more current. So that would say only a small push, only a small amount of energy is required to get the electrons flowing fast. There mustn't be a lot of opposition there. There can't be a lot of resistance in the circuit. So by looking at the slope of this graph with voltage against current, we can essentially work out how much resistance there is in the circuit. So to work out the slope, we take any point in the circuit. We take any point, on the graph. If it's a straight line, we can take any point, and we look at what voltage is going in and what's the current coming out. So I could take 3 here, for instance, and we go across. If we've got 3 volts applied to the circuit, it gives us a current of 1.5 amps. Okay, so we take the rise, how far we came up. So that's here to 3, the rise 3, divided by the run, how far across we came over here. So the run is 1.5, so 3 divided by 1.5, should be able to do that one in your head, is 2, okay, and so the resistance must be 2 ohms, is the unit for resistance. So the slope here is 2, and the resistance is the same value. We just add the symbol to tell us its resistance is ohms. Alright, And so again, just coming back to that really quickly, going over that one more time really quickly, a really steep line would mean that a large voltage is needed to generate a small current, to get a slow or a not so quick flow of electrons. That means there must be a lot of opposition, a lot of resistance. A really flat line would suggest that only a small voltage is needed to get a large current flowing. That must mean there can't be a lot of opposition or resistance in the circuit. And we can represent this mathematically too here. Remember we're basically saying the resistance, which we usually use the letter R, equals the voltage up here, we usually use V, divided by current. Now current, we couldn't use C for current, that was already taken, so whoever came up with this formula decided the letter that was available that made the most sense was I. Don't ask me why. But essentially what we're saying is that resistance is equal to voltage divided by current, which is actually Ohm's law, and my next video is on all about this, and you can rearrange this. But think about it. This makes sense. If we've got a big voltage, let's say 10 volts, and we're only getting a small current, let's say 1 amp, then we get a big resistance. It might be 10 ohms. Whereas if we do it the other way around, if we've got a small voltage, let's go 1 volt, and a big current, so we only need a little bit of energy to get them flowing really quickly, then we only have 0.1. We have a very little resistance. So it makes sense if we think about this formula. Basically, if we look at those values, what we're saying is that if we have a large voltage, but a large voltage only generates a small current, then the resistance must be big. And if we've got a small voltage generates a big current, the resistance must be little. And if you plug numbers in, you'll see that works. So the relationship can be represented by this formula, and that's called Ohm's law. And so if you get a question like this in a test, which you might, if you got it in this graph form, don't stress. You don't actually have to learn this kind of separately from the others. Just come back to that. If you can use Ohm's law and you know resistance is equal to voltage divided by current, just pick any point on the graph, like say here. We could have done 6 and come across and gone, well, we've got 6 volts, we've got almost 3 amps. And so we'll do 6 divided by 3, and that would give us the same answer, 2 as well. So you just take the voltage at any point divided by the current, and you should get the resistance. So you can use Ohm's law. You don't actually have to remember the graph separately. So I hope you found that helpful, and probably you want to go on now and look at the next little video on Ohm's law and some of the calculations we'll do there.